It's now my pleasure for our next presentation. We will address how to bin for profit, maximize mix and blend, and our presenter is Dr. Dirk Maier. Dr. Maier is a professor and post-harvest engineer in the Department of Agricultural and Biosystems Engineering, the Department of Animal Science, and the Department of Food Science and Human Nutrition at Iowa State University in Ames. At Iowa State, he is responsible for leading an internationally recognized research and outreach program in post-harvest engineering and feed technology applied to grain and feed operations and processing. He established the ISU Feed Technology Program and serves as the director of the ISU Feed Mill and Grain Science Complex. He was instrumental in establishing the Middle East and Africa Training Center for feed manufacturing in Tunisia and serves as its associate director. Previously, he was head of the Department of Grain Science and Industry and director of the IGP Institute at Kansas State University, where he was responsible for building the O.H. Cruz Feed Technology Innovation Center and expanded on-site and virtual continuing education and credentialing programs for grain, feed, and flour milling industry professionals. Dr. Maier is a registered professional engineer, a fellow of the American Society of Agricultural and Biological Engineers, and a member of and officer of several academic and professional scholarly societies. Let's give a big CONVEY welcome to Dr. Maier.
Thanks, Mark. Somewhere there's a clicker. Oh, there it is. They tell you to send a short bio, but you don't expect them to read it all, but thank you very much. It's a familiar group, and I appreciate the opportunity to be here. And it's great to be back at meetings in person, right? You all agree? Enough virtual meetings? Very good, very good. Yes, yes, yes. Thanks for the invitation, Jess. Appreciate it, and others that were involved in organizing this meeting. I want to talk a little bit. I just changed the title slightly. I say storing grain to maximize quality and blend. So mix and blend is kind of the same. Quality remains a really important topic. I mean, I've talked about this all of my career, and when prices are as high as they are, I think we're all getting a little bit more interested again in terms of how we need to maintain quality, how we need to minimize shrink, and how we need to reduce our cost and maximize our profit. And we have to go a little bit back to the basics, and we kind of start with that in all of our courses, and this is kind of just grabbing a few of the concepts that we normally teach over several days, is a basic concept called equilibrium moisture content. If you don't understand that concept, I always say in our classes, you are not going to be successful as a grain operations management person. And if you don't understand that, you're also not going to do very well in the allied equipment industry when you're trying to size fans, when you're trying to sell bins, or when you're trying to help people, select the right equipment. You have to understand that the equilibrium moisture content is the moisture content in which grain will equilibrate when exposed to particular drying and rewetting conditions, right? Either the grain will absorb moisture or desorb moisture, and if we don't understand the relationship and how that is different for different grains and how it's influenced by temperature and relative humidity, you cannot be successful in maintaining quality and optimizing your blend. And this relationship is of particular importance for grain cooling, drying, conditioning, and rewetting. One question that we can ask is, for fan operation management to cool, dry, condition, or rewet, given certain conditions of air temperature, relative humidity, what will the moisture content of the grain equilibrate towards? How do we manage shrink? And again, it's a function of these inlet air temperature and relative humidity, and specifically the dry bulb temperature of the air. And this is just one curve we call the cornicular moisture isotherm. Isotherm relates to one particular temperature. In this case, it's at 50 degrees Celsius. And it's a function of the ambient relative humidity versus the grain moisture content. And the red line just represents what happens when grain is at 50 degrees Fahrenheit. And so if we were to expose this grain, just like in this room, for example, and we have the air conditioner going here, and if it was 50 degrees and 70% relative humidity in the air, and we can measure that very easily, after some time the corn will equilibrate to 14 to 15%. Very basic relationship, right? And so now if I change this, keep the same temperature, if I change the relative humidity, now I'm at 30%, my grain will equilibrate to about 9 to 10%. It will not go down any further, right? If it's exposed to those conditions, that's what it will be after so many hours or so many days. It's not going to be higher, it's not going to be lower. And that's a fixed relationship. In the same manner, if I increase the air conditioning unit in such a way that I'm still at the same temperature, 50, but the relative humidity now is 90, that means my grain is going to be about 20%. It'll be at that level. It doesn't matter for any of for corn, for example, that's what it will equilibrate to. And that's a relationship that we have to understand how it relates to then operating our fans and minimizing our shrink. Another way to kind of think about that is to say, okay, now we put our grain in the bin. It's at 10% or 15% or 20%, and that grain contains a lot of air. And that's not even when the fan is blowing. This is just the amount of air. Let's say in the entire volume of that grain bin, you have about 35 to 40% just air volume, right? And that air equilibrates and interacts with the temperature and the moisture content of the grain. And so given a certain condition of grain temperature and moisture content, what's that relative humidity? And if you understand what that relative humidity equilibrates to, that determines whether your grain will spoil or not. So for example, if the corn is stored at 10% moisture content, the relative humidity in that air surrounding the corn at 50 degrees is going to be 30%. 30% is relatively dry. Grain will not spoil. When the temperature is, again, 50 degrees and the corn is stored at 15% moisture content, the relative humidity in the interstitial air is about 70%. Right? And that's kind of gets to be the borderline. You get much higher in relative humidity, such as, for example, at 90%, above 70% relatively, you basically trigger mold spores, and mold spores result in spoilage. So it's a very simple relationship that, generally speaking, throughout most of our Midwestern region, we have very good weather conditions for us to store grain at around 13% moisture soybean, 15% moisture corn. If you're over here in Nebraska, Kansas, and places, you also have wheat and sorghum. You have a little bit more of a complicated mix with regard to grain preservation, or you go a little bit further north in the Dakotas and get into some of the specialty crops, different relationships for sunflower seed and pulses and so forth and so on. Again, every one of those have a particular moisture relationship. As a matter of fact, that's captured in this slide right here. We have wheat on there, soybeans, corn, sunflower, and rice. And grain composition type, the amount of starch, the amount of oil, determines the relationship. And the higher the oil content, for example, the higher the EMC. And the higher the EMC, the more spoilage prone it is when you have a higher oil content grain. So when you take a look at that, corn, wheat, rice, 13% moisture, 65% relative humidity, less than 10% oil content, usually very easy to store in comparison. Soybeans, oil content 20 to 25%. Got to be careful at 13% moisture, but the relative humidity in that grain will be about 70. You get to sort of a borderline, depending on temperature. And then when you have sunflower and canola at 45 to 50% oil content, for example, if you were at 13% moisture content, the relative humidity in that air around the sunflower and canola would be about 90%, and that would trigger mold spores within about 3 to 4 weeks. And that's why you get I was talking with a fellow who's out there on the salvage side, and of course, that's what he does. He recovers stuff when we screw up, right? And it's like, that's what we want to prevent, right? And we had a good brief conversation about what my goal is and what his goal is, and they're opposite, right? But I respect the fact that that we need to have that, but ideally we would want to prevent it in our industry. So equilibrium moisture content relationships are grain specific. This is what we want to prevent, right? I wrote an article in World Grain that came out in the recent issue in terms of how bin fires occur, right? And till you get to that smoldering effect or that breakout of a fire, it's a biological process of spoilage. When you have a fire in grain, you screwed up, right? You allowed molds to get away from you. It should never happen. It should never happen in a storage mass. We have way too many tools to monitor today, from temperature to moisture cables to CO2 and otherwise. We should never have these kinds of situations happen in our facilities anymore, given the tools that we have available to monitor and then to manage. So how can we determine safe storage moisture content? It's very simple. Again, relative humidity of the air surrounding the kernels, 65 to 75%. Anytime higher relative humidity around the grain, molds will be triggered within a 3 to 4 week period. And that's why above about 65 to 70%, we have unsafe storage situations, and below, it's pretty much safe to store at any temperature. And so again, you see the cereals around corn, wheat, rice are relatively easy to store around 13 to 15% at most temperatures, because it is a lower relative humidity relationship. And then again, on the, this is a real sensitive clicker, so sorry about that. And then safe storage conditions that you'd have on sunflower and soy has to be lower with regard to that moisture content. Now, if I confused you, hey, now we have an app, right? So you don't even need to look at the charts. You don't really have to pay that much attention to me here this afternoon, because we developed an app called the Grain Aeration Storage app. It's available for all Android phones. There's an older version available. It's called the Cargill Aeration app on iPhones. We will soon have the iPhone. I keep saying that, but it's a licensing deal. So with Apple, it's just a little bit more complicated than with Android. But this app will also be available for Apple phones very soon. And allows you for cooling, aeration prediction, aeration weather forecasts, and air grain moisture relationships. And that bottom part is essentially what I just tried to explain to you. And this new grain aeration and storage app, if you look at that, says if you want to know what the equilibrium moisture content of corn is, you put in the temperature, you put in the relative humidity, you click on results, and it tells you it's 14.8%, right? That's it. So you have it right at your fingertips. The same thing if you want to know what the equilibrium relative humidity, that air condition is surrounding the corn, right? You put in there the temperature of the corn, the moisture content of the corn, and it'll tell you it's 70.3%, right? 72.3%, which kind of gets to the borderline at 50 degrees, right? If you lowered the temperature 30 degrees and 70 and 15% moisture, the relative humidity would be lower, would be safer to store, right? And thirdly, which is really slick, you can say, hey, what is the safe storage moisture content for corn at any temperature? Here in this case, 52, and they'll tell you it's 14.2%, all right? Boom, app. No more questions. The answers are right there at your fingertips. If you don't use that, I can't help you any further, right? I mean, now you have all the tools. Monitoring tools, apps. I don't know what else I can get for you. It just took a few years to get to this point, but now it's there. So let's remind ourselves of these best practices too. We'll go through those. Sanitation, loading, aeration monitoring. Many of you have heard me talk about this many times. But just as a reminder again, sanitation is pest control, cleaning up, keeping structures clean is very important. Even more important this day and age with carryover, with traceability, with other types of aspects. We've got to pay more attention to that in the grain handling side of things. And we've got to pay attention to how we load and fill our structures, screening and pre-cleaning, particularly coring, and I call it unpeaking now, right? Coring, unpeaking. Take that peak out, take the core out. Takes maybe a one-time core or multiple withdrawals. Leveling, you see these mechanical spreaders, the spider spreaders and so forth, which is great to see those advances as well, or they have their place. And then, sealing to prevent air leakage is very important. Core fines, you have foreign material, broken grain weeds in the center. You're not going to get the same amount of airflow through it. It just can't, right? More resistance, more time. So if you want to keep paying the electric utility company twice the electric charges that you should be paying them if you core, fine, I can't help you, right? But if you core level and you get uniform airflow means uniform cooling. Uniform cooling means shorter cooling times. Shorter cooling times means less electric power, less energy consumption, lower cost, right? You want more money in your pocket. You want to increase your margin. You've got to reduce your costs. One way to reduce your cost is run your fans fewer hours, and you can do that by unpeaking, right? Unpeaking. Here's just an example of data that was generated a number of years ago, and it shows the feet per minute. This is the air velocity through peak grain versus at the sides. You can see the factor of 15 to 20 times, right? 15 to 20 times slower is directly proportional to cooling time. Airflow rate is directly proportional to cooling time, right? A tenth of a CFM per bushel, minimum 150 hours of cooling time. If you only have a 20th, it takes 300 hours. You decide, right? 150 hours through the rest of the grain mass, 300 hours through the middle. The kW you're paying for is ridiculous, right? So you can avoid that. Unpeak your grain. One-time coring or multiple ways. Just enough so that you get more uniform airflow through the grain mass. That's all we're talking about. And you can do that as you fill throughout the season, as you have opportunities to ship, as you have opportunity to take out some of that grain in the core. Aeration. Always lots of questions about aeration. Selecting proper ambient air conditions during fan operation hours is critical for avoiding overdrying during long-term storage. So when we have, in this case, we've got an example of 68-degree air coming in the bottom, 60% relative humidity. Well, 68-degree air at 60% relative humidity, if you went to the app, it'll tell you that the moisture content will shrink to, in the bottom layer, to about 11.8, 11.9, 12%. So that means that moisture that's being picked up from this 14% moisture corn is going to be in the air going up through the rest of the grain, and it'll be sort of in equilibrium at 14, and then as it exits, and it might be at 80% relative humidity, it'll have 16% at the top. Now, if you add condensation to that onto the grain surface, again, you got mold triggered because of higher relative humidity, moisture condensation, and this is where all the surface crusting comes from, right? Again, surface crusting is just a biological process of mold spores developing and making the kernels stick together. That's it. There's nothing else in the grain that makes that grain kernel stick with each other. Mold spores, that's it. You activate them, higher relative humidity, warmer temperatures, they will grow, period, right? It's just a biological process. And so you need to avoid that. Now, all right, got to show you this chart, right? Because the question is always, what will something cool to? So on this chart, and I know green's sometimes a little bit of a hard color to see, here we have wheat and air at equilibrium and at 12% moisture content. That's what that green line shows. And the question is, if we aerate wheat 12%, 95 degrees, with air that's 75 degrees Fahrenheit, dry bulb, and 80% relative humidity, which is something you can get off your local weather report, what will that wheat cool to? Right? I can tell you how long it will take, but what will it cool to? It will cool to, on average, to the average ambient temperature and relative humidity. And so what we first need to know is what is the wet bulb temperature, 70 degrees Fahrenheit. And it's this line right here on this chart, 70 degrees, that's the air conditions right here that are entering the bin. And these are the grain conditions right here at 95 degrees and 12% moisture content. And so cooling of grain takes place at the wet bulb temperature. Those of you who've never heard of it, well, come to our class and we'll explain it to you a little bit further, right? But grain cools along the wet bulb temperature. And that means that this grain at 95 degrees and 12% moisture content is going to have to meet this line of wet bulb right here as a result of what these inlet temperature and relative humidity conditions are. And that means that this wheat will cool to 82 degrees. Dirk, you mean to tell me that I'm blowing 75-degree air in at 80% humidity and it's not going to cool to 75 degrees? No, it'll cool to 82 degrees. That's just the way the psychrometric works with regard to that. And this little thing called the equilibrium moisture content relationship, which I was mentioning to you at the beginning of the talk. And not only will that happen, but the grain moisture content of that 12% moisture wheat will trend towards 16.9% as a result of these inlet conditions. If we have corn at 16%, 75 degrees, aerated with air at 60 degrees and 50% relative humidity. Again, we need to know at what is the wet bulb temperature. The wet bulb temperature is 60 degrees and 50% RH is 50 degrees Fahrenheit wet bulb. That means that if the corn is at 16% here on this line, the cooling air is coming in at 60 degrees and 50% humidity. Cooling of that grain has to take place along this wet bulb temperature right here, and the corn at 16 and 60 is right here, okay? So cooling has to take place under these conditions. So air is coming in, and it's going to cool the grain to 54 degrees. You say, Dirk, you were blowing in air at 60 degrees and 50% humidity, and you're telling me the grain is going to cool to a lower temperature than 60 degrees. And the answer is yes, it'll cool to 54 degrees because it's cooling at the wet bulb temperature, and it's going to be taking moisture out of your grain because of the EMC relationship, because it's shrinking that grain on that bottom layer to 11.9%. It's an energy and mass balance. Well, guess what? You probably ignored just what I told you here the last 5 minutes. I got an app for you, all right, that will do that for you, okay? This app is called the Cooling Aeration app. It's one of those 3 modules in the app, okay? It says, okay, you want to put corn in there, grain moisture is 16%, target moisture is 15. I just made that up, but that's a good number. Grain temperature is 75, air temperature is 60, air is 50, and I'm cooling with 1/10 of a CFM per bushel. And the answer is when I click on results, it takes at least about 180 hours. It'll shrink towards 11.5. I had on the previous slide 11.9. This is a result of the number of hours running. And it basically also says, hey, you know, if you want major drying, this is not a good idea, right? It'll give you a red indicator. Small drying effect, sort of a greenish, yellowish. Air conditions are unsuitable because of this shrink effect, right? So it gives you an orange indicator, but it'll really give you a good cooling effect, so that's a green. All right? So no more complaints. You can basically predict what your grain will cool to, what it will shrink to as a function of air rating. And the same thing for the wheat example here. We've got 12% moisture. I said target at 12. Grain temperature 95, air temperature 75, air relative humidity 80. We still have 1/10 of a CFM per bushel, which is high in wheat. Will give you quite a bit of horsepower required. 165 hours. You'll be getting major rewetting. That's why you have the red button there, right, or indicator, 16.8% moisture addition to that. Lower. Moisture always takes a much longer time. Target moisture, would not change. Air conditions would be unsuitable because of this rewetting effect, but you will sure cool the grain from 95 to 83, so that gives you a green button. Okay? So here's the app, but you ought to understand a little bit about what the calculations are behind that. So, okay, how do we decide to turn on an aeration fan? This is a typical matrix. You see that at times. And up here in this upper layer, the air is much warmer than the grain. You typically don't want to aerate to warm things up. We don't want to warm grain up. I'll get to that. Air is much cooler than grain below that blue line. And of course, it can be at high relative humidities. It can be kind of risky, right? Because we're blowing even cool, high humidity air in there unless we intentionally want to recondition the grain. But otherwise, we create this high relative humidity environment. That's why this is labeled risky aeration. And then maintenance aeration, if we're really not changing anything in temperature, right, and at moisture. And so ideal aeration, if you really want to make some progress, is when you have relative humidity conditions that are kind of in equilibrium of the target that you have, for example, with 15 corn or with 13% soybeans. So again, this is just to kind of illustrate and put us kind of on the map with regard to these differences in the relationship between temperature difference and relative humidity. This is a recommendation chart that Ken Hellevang from North Dakota developed a number of years ago. We use it in training all the time. If you really have a thermostat that you manually operate, or you basically decide to go out and turn the fan on, or use some automation system, you can accomplish cooling in 2 or 3 steps through most of our region. Get down to temperatures in the 30s or so. North Dakota is awfully cold, so Ken shows us here that if you get all the way down into the low 20s, you'll actually kill insects, which can be a good thing. But Ken also says, well, you may need to warm this back up in the spring and get it down into the 35 to 40 degrees. I don't quite agree with getting it quite that cold. We don't need to do it in Iowa. We don't need much of Iowa. Northern Iowa is a little bit different. We don't need to do it in Illinois. If we cool around 30 and keep that grain cold, we don't have to aerate in the spring. We don't want to aerate in the spring to warm that grain back up. Really not a good idea, and I'll show that to you here in a moment. So, general recommendation, from weather conditions average across the Midwest, can get down in the 40s in October and 30s in November and around freezing in December. That's kind of the patterns that we're after. Then we do maybe some maintenance aeration in the wintertime to keep temperatures around maintained. And then in the springtime, we'll keep our cold grain cold. We'll seal our fans. We ventilate our headspace intermittently. We've unpeaked, right? We've got good quality grain in storage, and we can maintain because grain is a very good insulator. And part of the sealing effect is you got 40% air volume in there, right? And if you don't seal your fans, you just have a pump going there as a function of wind, as a function of blowing past, and you're just warming that grain up prematurely if you don't seal your fans on the bottom. It's just like a fireplace, right? If you don't, close the shutter again in the wintertime, it sucks all the heat out of your house. Now, here's a rule of thumb for aeration shrink. Different companies have different shrink equations, but this is one that the Andersons have used for a long, long time. Bushels aerated times degree temperature drop times this magic factor of 0.022 that nobody seems to know where it came from, times 1.2%. That is kind of how they predict their shrink. And so I had to kind of work this equation backwards to see, well, does that make any sense? So when I used the example, and I used our cooling equation examples and said, if I have 50,000 bushels of corn at 15.5, moisture content and 70 degrees, so I'm in the early fall after drying, and I cool that on average with 50 degrees at 75% humidity, I shrink 264 bushels out of that in the October cycle, and that gets me down to about 15.2%. If I cool it another 10 degrees later on, at about 69% relative humidity, that's another 131 bushels of shrink. That gets me down to 15.1. And if I cool down to 30 at 64%, another 131 bushels of shrink gets me down to about 15. So I could follow that equation. I don't know how they did it back in the 1960s when they came up with that equation. At the Andersons, either nobody wants to say it or nobody knows anymore because the people have long gone or passed. But that factor's been around for a long time. And so the total shrink I can predict with these cooling apps about 526 bushels, and that gives me to this expected final moisture content of 15 to 15.2. So it's a pretty good rule of thumb that seems to work. And again, the apps can get you in that direction as well. The aspect is moisture loss due to excessive aeration. If you don't pay attention to how you aerate, you can end up with highly overly dry corn, and it's really difficult to get that moisture back. And every bushel of water is the same value as every bushel of corn, right? Where are we at? $7, $6, something like that. Soybeans are $14. That's real valuable water, right? Electricity is cheap in comparison to that. And when we just multiply that out, we did it on a 60-foot diameter, 45 sidewall with a proper fan sizes at the kilowatts that we did, 84-foot diameter, 75 sidewall height, 105-footer, and that's big money in terms of that loss. And that's only at $4 a bushel, so you can basically double that right now, right? And it's hard to get that back. If you do it more with paying attention to the equilibrium moisture content, then we talk more controlled aeration, and you might end up with this type of range, 14.8 to 15.5. It's not going to be perfectly uniform, but as you start unloading that, your average is going to come out on 15%. So we can do well with this kind of an aeration scheme. And you can see that there's a savings of 6x in terms of that shrink loss in comparison to that shrink loss where you have a bottom layer of 14.9, a top layer of 15.5, versus a bottom layer of 10% and 15.5. And the same thing is, okay. And so one of the other aspects then to keep in mind, and this is sometimes a little tricky to get your mind around, but the basic point here is when we aerate at any initial corn temperature, right? It's really the equilibrium conditions of the air that determine what the moisture content will be, off the grain. So if my air conditions are 50 degrees and 60% humidity, again, you can go to the app and it'll tell you that the moisture content of that grain will equilibrate towards 13.3. And so it doesn't matter what the initial moisture content is, and it doesn't really matter what the initial temperature of the grain is. It will equilibrate to 13.3 eventually. The only difference will be what the final temperature of the grain will be. So everything that's indicated here in yellow tries to put moisture back into the corn, right? This was 13 initially, and here we would be aerating with 13.3 to 13.3. If the relative humidity is 80%, we would be driving it towards 16.5. That would be higher than any of these initial moisture contents. And the same thing is when we have 40 degrees and 60% humidity, or 40 degrees and 80% humidity. Again, it doesn't matter what the initial temperature of the grain is. It's a function of the equilibrium conditions that the air conditions cause to come into contact, with the grain. So at the same thing on the soybean side, again, that can be very expensive in terms of shrink if it's not controlled with regard to paying attention. The same conditions, you're talking a much bigger dollar item. That's only at $8 a bushel. You can multiply that by 1.5 these days. And again, if we can pay attention to that and minimize the amount of shrink, maybe end up with 12.3 to 13. Again, you can create your own scenarios, but this is practically achievable. Then again, the shrink loss difference or savings is a factor of 6x. That's a lot of money, right? That you can impress your boss with that real fast, right? And we've had people that started paying attention to that, and they come back and said, well, it works. Yeah, it works. I knew that, but it works for them, right? And all of a sudden, their shrink has gone down, the amount of kilowatt hours that they're paying for has gone down, and this is the way to maximize your gross margins at your facility, paying attention to that moisture balance in your grain mass. Same thing here for soybeans, same example, 50, 60, 80% humidity. If we start 11% to 14.5, you either shrink in moisture or you increase moisture. The good news is when you really look at 50 degrees and 40 degrees and 60%, 80% humidity, it's a fairly narrow range. And that kind of keeps us in that 15% moisture content corn, that 13% moisture content soybeans. And it should work for most people, actually, fairly successfully, given the weather conditions that we generally have. Guess what? There's an app, all right? As a matter of fact, the third function of this app is, okay, if I really want to know what happens to my grain, I now have this weather forecast. It literally goes to the weather forecast at your local, wherever you are, right? Mine came up for Omaha, right, because I'm in Omaha right now. You can aerate grain today in Omaha? No, not a good idea because it's too warm and the relative humidity is too high, or whatever it is, right? And so this will give you a forecast over 6 days to indicate what your average minimum temperatures will be and whether this might be a good time to aerate or not. And it breaks it down by hour, essentially, right? So, and it also kind of gives you an idea what you might want to set your thermostat at, right? If you want to turn the fans on, you don't want to hunt every hour. You want to say, hey, turn the fan on and run as long as the temperature is below 50, right? And so as soon as it hits that, in the evening when you're gone anyhow, you want that fan to come on. It'll run until 8 o'clock in the morning till you show back up to work because the temperature is going back up above 50, right? And it will have taken care of that, right? And it'll come back on whenever that temperature has been reached. It's very simple, thermostat, right? We don't need much more than that based on our weather conditions here in the Midwest. So this app will give you that. So here's the app, Des Moines, Iowa. I said a fan run time of 50%. In this case, it brought up my historic weather forecast, right? My historic weather conditions. When I pulled it up, it was average 60 degrees and minimum temperature 45, right, in this particular time of the year. Sorry. And it would have basically said, hey, set your aeration thermostat to about 60 degrees. That's the average temperature. And over the next 6 days, you would accumulate 129 hours on the 15th day. This is the date of the day. The 16th, it's today the 13th, it's just a coincidence. So this would have been last fall sometime. It said on the first day, the 15th, you have 24 hours in the day, and you'd have 24 hours that the aeration fan can run because all 24 hours are below 60 degrees. And you have that then accumulating on the third day, which is 17th. It said it was only 14 out of 24 hours, so you'd be at 62 hours, 19 out of 24, so there's a couple days where it would not work. But 129 hours is a long ways towards the 150 minimum that you need to get a cooling fund through. Again, you can use the app. You can update it every day, and it'll give you the next 6 days, next 6 days, next 6 days. And if you click on the date, it'll break out the 24 hours and tell you exactly on which hours it's red versus yellow versus green. So very slick. So no more complaints. Use the app. All right. And then you can answer this question too. Should cooled grain be warmed up in the spring? This is always one of those questions, always comes up, notorious. And this is part of the old recommendations that you see in a lot of illustrations. Yeah, warm the grain back up. It's like, no, don't warm the grain back up. Here's why. We always look at weather conditions. So this is 5 years of average weather conditions in Des Moines. Wherever we go and do a training, we'll pull it up. So we've done it for Bloomington. We've done it for other locations. And the blue line is the temperature. The yellowish line is the relative humidity. Temperature's here on the left. Relative humidity is on the right. If we take the average of 5 years, right, it will give us 52.2 degrees plus minus 19. That's the 5-year average for the year. Relative humidity 70% plus minus 6 percentage points. It's a pretty good place to store grain. This is the monthly 5-year averages, right? So it's taking the 5 years and averaging them over 5 years. And so again, we see that in the wintertime, the blue line here, up January, really from late October, November, December, we get to fairly low temperature in the wintertime, below 40. Fall and spring, 50 to 60 degrees. Summer, 60 to 80 degrees. The same thing with the relative humidities. It should not be hard to store grain in Des Moines, Iowa, right? So if you screw it up, you need some help, right? Because the weather conditions are pretty good. The same in Bloomington, Illinois, we learned that too. So we then calculate, the green line here is the equilibrium moisture content relationship. Yellow line is the soybean. I'm trying to even color code it, right? Greenish corn, yellowish soybeans. And this is the wet bulb temperature. Remember, grain cools as a function of the wet bulb temperature. And so when we look at that, on average for the year in Des Moines, 5 years, 14.7% corn. If you're shrinking corn below 14.7, you're not doing a good job because weather conditions are such that you should be able to maintain 15% moisture content in Des Moines. And you should be able to maintain soybeans at 13%. That's the nice weather we have, right? So it should work. And so one of the things that we've done is, okay, so now what I'm doing here is I use the app and I've followed the grain throughout the year. So in this case, for Des Moines, again, over the 5 years, I say, hey, if my grain moisture content is 15, coming out of the dryer, put in the bin, my grain temperature in the bin is 65. Now, in November, right, my average temperature in November is about 40 degrees, and my air relative humidity is 70.5. If I aerate this grain with these conditions, right, if I aerate this grain with these conditions that I have on the 5-year average, I'm going to end up with these conditions right there, as a matter of fact. Sorry, I can't see that angle quite as well. But this result will tell me that on average in November, I'd be at 15.3% and 40.6 degree temperature. Now I'm going to take these conditions and I'm going to carry them into the wintertime, and I'm going to pretend like I'm not going to aerate in December and January, but I'm jumping ahead to February. So I have these conditions of 15.3 and 40.6. Now I'm aerating with 26.9 degree temperature, 72% relative humidity, and I'm going to end up with 16.4 and 27 grain temperature. So I'm trying to put moisture into the grain in February. So I want to get my aerations done in November, December, January, right, before I'm trying to put moisture back into the grain. And again, here's, if I go into April, now I would be warming things back up because, right, I have this nice cool grain below 30, and I have on average 52 degrees. So it makes no sense to turn aeration fans on, right? Because I'm warming the grain up. It's just a natural process. And when I do, I'm going to shrink it down to 13.4, and the grain temperature will be warmed up to close to 50. It's not good. Right? It's not necessary. It's not necessary if your grain is in good shape, if you've aerated properly in the fall, if you've unpeaked it, if you've taken the core out, and if you've been monitoring it with CO2 and it is pretty stable, right? So, and then we follow it all the way in July, of course. Don't want to aerate in July, right? It gets plenty warm. Cold grain stores well. It may warm up on the sides, but if your moisture content is low enough, it's not going to create moisture migration patterns. It's not going to have moisture moving unless you have condensation in the headspace. So spring aeration, no. Doing okay with time? Okay. So seal your fans. Seal your fans. Do a good job with headspace ventilation. This is the right type of setup. I see a lot of bin companies represented. You're doing a better job. Thank you. You've improved the industry over the last several years because these are still systems that are sitting out there on a lot of roofs, and at some point somebody designed that, and that was not good. And even now, somebody designed this great big bin without roof exhausters. What in the world? This was just in your magazine a couple of years ago. What? Who does that? Add roof exhausters around the entire peak, not just on one side. That's not a good idea. All right, what about grain piles? Big pain. Hey, guess what? The same weather conditions apply, except now you're running the fans all the time, right? So on average, the grain is going to follow this pattern. That's what the grain is going to follow. So if you aerate into March or April and haven't picked up your ground pile is going to follow the green line in terms of moisture content and the bluish line in terms of grain temperature, right? So what I've done is I've looked at the weather data here just from October through March, and in October through March here in Des Moines, I'm on average 36.2 degrees, so that's good for a pile, right? Relative humidity on average is 71.3, so my EMC in corn, sorry it says maize, should be corn, 15.7, soybeans 13.9, so wet bulb 33. Okay, October through March, that's about your margin, right? You don't want to really extend that beyond that. Tell your merchandisers, don't do it. Huh? Because that's really all you have is from November through March. And you've got plenty of time there to keep it below 40 degrees, right? 300 hours of aeration time each month if it's at 50% time. So it'll stay cool. But what it will not do in the summertime, right? If you're in the summertime or in this period from April through September, average temperature in Des Moines over 5 years is 68 degrees, 69% humidity, and you shrink it down to 13.7, 12.5. Okay, maybe you want to shrink it, but you're also going to potentially spoil it during this transition from cold to warm. So there's just not, don't extend that time. I'm going to skip over that because you can now do that because you have the app. So managing aeration shrink loss, I've got a few more slides here. Aeration cooling of grain follows the wet bulb temperature. For given air properties, the dry bulb temperature of grain will cool to, and the moisture content the grain will equilibrate towards can be calculated. And now you have the app. Shrink loss due to aeration cooling can be calculated based on evaporative cooling effect, and then the shrink loss costs include not just the moisture loss that I showed you, but of course also the electric fan energy due to excessive operation. Last step. Monitoring. Oh, so much technology coming out. It's wonderful. But temperature cable patterns. I don't have enough time to really go into this, and if any of you are temperature cable representatives, I apologize in advance, but this is what you say, right? I'm reading your literature. As a rule of thumb, one cable monitors a radius of 9 feet. 9 feet, one temperature sensor. Really? That's how we're placing temperature cables, right? Wow. Think of the roof loads that we add. If a sensor is typically 7 feet apart along a cable, and even if we assume it's 3.5 foot radius, right, without overlapping any sensors, if I calculate, I had one of my students calculate, say, okay, I want the calculation. In this type of a pattern, according to this placement, there's no way that the grain would cover 50 or 100%. As a matter of fact, the grain would only cover, the cable sensors would only cover 1.5%, 4.6%, or 10.8% of the grain mass volume, according to the sensor placements. If you assume that a single sensor takes a 7-foot volume of temperature reading, and you put them in like Christmas tree balls, right? So something then that's not, doesn't work that way. We've done some calculations on how many cables. So I put 3,000 in a computer model. I put in 3,000 temperature sensors, and on average I get 27 degrees during the storage period. If I only put 15 sensors in it, I get 24 degrees. If I put 30 sensors in, I get 18 degrees. Wow, 3,000 versus 15, and you almost get the same average temperature. We got to be thinking about what do we really want to use temperature cables for. I'm not against temperature cables. I'm all for it. But what we want to use them for is to monitor cooling fronts, not to find a storage problem. That's like finding a needle in a haystack. It doesn't work unless the sensor is right where the problem occurs. So there are different sensors, different systems available. I'm not promoting any particular technology, but these are some nice things that are coming out. They're literally plug-and-play type of systems that monitor temperature, relative humidity, CO2. Very exciting new technologies. They show up on your cell phone. They go well with our app types of applications, and you don't have to run a lot of conduit to them. It's very exciting stuff. We have a number of those at our storage bins, not at the new site yet, but at these. And very simple fan control system. You basically plug them in and you can control your fans. And you can calculate the EMC of your headspace, and controls all those sensors. It's easy installation, very serviceable. Big advantage, no cables in the grain mass. Big disadvantage, no cables in the grain mass, right? Or you make them work with a certain number of temperature cables that it makes sense with. We've done some testing on the CO2 sensors, tried to see whether we can fool it, and within 3 weeks, put water on grain, within 3 weeks, you get CO2. The sensors don't lie. It's biological activity on the grain surface, all right? On the other hand, when we did something in the fall where something occurred naturally, we turned on the aeration fans, we cooled it out, we took that spoilage potential out. CO2 readings, January, February, March, stable. So we caught it. Never caught it with the temperature sensors, but we caught it with a CO2 sensor. Very simple technology, very effective. Handheld sensors. I've used and bought the same sensor for the last 25 years, and it's gone down in price. Can you believe it? It's gone down in price. $50. It used to be $4.99. Anyhow, it's good. Here's kind of the interpretation of the CO2 readings. Many of you have read those, and based on those, you don't want to overreact, but it can catch active grain spoilage for you. So stored grain conditions can be monitored with temperature, moisture, and CO2 sensors. Regular monitoring of stored grain conditions allows for early spoilage detection, and early detection of spoilage using CO2 saves time and money. Even some of the new cable technologies provide plug and play for that type of monitoring. That you can prevent with CO2 monitoring. So, best management practice: prepare, clean your storage bins for new crop harvest, dry grain, then store at safe conditions. Core and unpeak your grain mass after loading, aerate to cool, not to shrink, then seal your fans, manage your headspace conditions, and monitor your grain regularly. Thank you.
First, I want to thank you, Dirk, for everything. Like I say, I've been following that for 20 years, and I know you've saved me a lot of spoiled grains. You're preaching to the choir. But a couple questions I've got on our bins that we put the aeration controllers on and use the equilibrium moisture content. We were finding, because in Michigan of the humidity at dawn, we were turning our fans on 300 times a month on and off. And our electrical company swears they don't charge for the inrush, but those 50 to 60 horsepower fans will go up to 500 amps at inrush and then drop down, and we're starting them.
Yeah.
And in 2 years ago in March, we were warming up about 1 million bushel of wheat that we had to ship. And that's the other thing. If we try to ship cold grain, we're going to get moisture in the car. And my electrical bill went up by $20,000 that I couldn't explain. DTE swears that they don't charge for inrush, but that when I turned them off, that number went away. How should I adjust my temperature window and my moisture window to try to minimize those cycles of on and off.
Well, I think, you know, some of the older controllers, when they kept track of the relative humidity in particular, you get almost too many, on-off operations or cycles, right? And so that's why I kind of said, hey, with this app and going back looking at the weather data, just a thermostat-based probably will do it. Now, I know you've got a whole other challenges with some of your specialty grains and otherwise, and so you've got to tune in to moisture content very particularly. But I would maybe see whether you can focus a little bit more on the thermostat type settings versus doing EMC. That's what I would do. Yeah. 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 I mean, the EMC controllers were the old Sentry packs, and they did exactly what you're describing. And so it's more than what you typically need in that regard. That would be my recommendation on that. Thank you, Chuck.
Any other questions? Okay.
All right. Hey, thanks for the
All
opportunity.
right. Thank you, Dirk.
All right.
Appreciate it.